In this video, we're going to learn how to find the intervals on which a function is increasing and decreasing using the first derivative test. Let's start by looking at this picture of a function, y equal f of x. And we see that the function starts off increasing on the left, and when it reaches this point, c1, it decreases, and here it starts increasing and decreasing and increasing. Now, these highs and lows are called relative max points and relative min points. Relative maximum here, and relative minimum here. All right, so what we want to do is we want to find these values where a function is reaching maxes and mins, and on which intervals the functions are increasing and decreasing. And this will have to do with the first derivative. Well, we'll see that if the first derivative is positive, then a function's increasing. So like on this interval, it does look like the tangent lines have a positive slope. Okay, that is first derivative positive, and that's where a function's increasing. And here it looks like tangent lines have a negative slope, and that means negative slope is means first derivative negative, which means function's decreasing. Okay, so basically that will be based on the first derivative, and the sign of the first derivative we'll be able to see where a function's increasing and decreasing. So here we have a theorem that tells us just that if the derivative is positive, greater than 0, that means that the function is increasing. And if the derivative is negative, that means the function is decreasing. Function increasing means if x1 is less than x2, then f of x1 is less than f of x2. So the function basically is going up. Decreasing, well, again, if x1 is less than x2, then f of x1 is bigger than f of x2. That's what we mean by decreasing. So this theorem is proved using the mean value theorem. All right, so let's just look at it briefly. And we'll just look at the case where f prime is greater than 0. So suppose f prime is greater than 0, then the mean value theorem says that there exists a value in between x1 and x2 where f prime is actually equal to this slope, f of x2 minus f of x1 over x2 minus x1. Well, if we're assuming that f prime is greater than 0, that means this slope equal to the f prime of c would also be greater than 0. Okay, this is greater than 0, so this slope must be greater than 0. Now, if we're assuming that x2 is bigger than x1, so this is greater than 0, that means the top must be greater than 0. If the top is greater than 0, then f of x2 is greater than f of x1. And that's basically the proof. All right. Now we call these c values that we pictured here, all these c's, they're basically called critical values. C is a critical value of f of x. If f of x is continuous at c and f prime of x is 0 or f prime does not exist. Now back in this picture, at these three max mins, it looks like f prime is equal to 0. Here it looks like the tangent line is horizontal here, here, and here. At C4, the function comes to a sharp point, so here it looks like the tangent line doesn't exist, or f prime of C4 does not exist. All right, that's what we guess from these pictures, and here we have f prime is equal to 0, like f prime of C1 equals 0, and these two as well. Okay, now we ask the question, what might f of x look like at a critical value? So in this picture we see four typical possibilities. At the critical value c, f of x might have a high point if f prime of c is 0, and if the function's climbing on the left and going down on the right, then that would be a high point. All right, that means f prime greater than 0 on the left, less than 0 on the right, then we have a max. All right, and if the opposite is true, less than 0 on the left, bigger than 0 on the right, that is descending and then going up, then we have a min. Again, we're assuming f prime is equal to 0 here. Remember, critical value means f prime equals 0 or f prime does not exist, but the function f of x does exist. All right, here's another one. Here, this function comes to a point, so we're assuming that f prime of c does not exist here, and we get this relative min. Now here's another place where f prime of c is equal to 0, and yet we don't have a higher low point. You see, we do have this horizontal tangent line, f prime of c equals 0, but here the function's climbing, flattening out, and continuing to climb. So this can happen as well. So if we're in this situation, then to the left, f prime is greater than 0, and to the right, f prime is greater than 0, and then we don't have a max or min at that point. In order to have a max or min, a max or min, f prime has to change signs. Here, f prime changes signs to the left and right of this c critical value. It goes from positive to negative, and here it goes from negative to positive. So it has to change signs in order for the critical value to be a max or min. Okay. Now here's the first derivative test. So they're just summarizing. It just summarizes really what we've seen or discussed just now. The first derivative test is for where a function's increasing and decreasing and for relative max and relative min points. So first what you do is you place critical values on the number line and all zeros of the denominator. Those are not critical values, but you put those on the number line as well. Okay. And then you see here's if to the left of the critical value and the right of the critical value you have a change in sign, then you're going to have a change in sign of f prime, then you're going to have a max or min. If the change in sign is positive on the left, negative on the right, it's a max. If it's negative and then positive, it's a min. Now, that's not something you have to memorize. What we do is we just draw a little diagram like this. For f prime positive, we do a upward slope, and for f prime negative, we do a downward slope above it. And then you see that it appears that the function's going up and down, and then it appears that we're having a max. And here, f prime less than 0, we draw a downward slope. That is, our function f has a downward slope. And here, if f prime is greater than 0, our function f has an upward slope left to right. And then it appears that we have a min here. So this little diagram helps us realize whether or not we have a max or a min. Now, if this is a situation that the function's positive, that f prime, is positive left and right, then we don't have a max or min. Or if f prime is negative left and right of the critical value, then again, we don't have a max or min. So that's called the first derivative test. And it gives us where the function's increasing and decreasing, because wherever f prime is positive, we have increasing. Wherever f prime is negative, we have decreasing. And it also tells us where we have maxes and mins. So now we're just going to apply the first derivative test to some functions and figure out all this information.